To the second session. Yeah, please let's start with the first talk on ILA.
So I will present an intermediate language for fully homomorphic encryption, and by the end of this talk, I hope to convince every one of you that like even complex cryptographic techniques like homomorphic encryption can benefit from basic PL theory. So let's recall what is homomorphic encryption. Homomorphic encryption is like we would like to perform some arithmetic operations on some data, like for example m and m prime could be real numbers or integers, and we would like to compute the product of m and m prime, but we don't want to don't want to give anything about like m and m prime. So what we do is like we encrypt m and m prime, and we do some homomorphic operations which is equivalent to product on these encrypted data, and the idea is if we decrypt it back, we should be able to get the product. And homomorphic encryption is finding some applications in privacy preserving machine learning. It's like whenever there is like some privacy and we don't want to disclose data, homomorphic encryption can potentially be used there, and also it has like some interesting applications in decentralized finance. So I will start with an example. We wrote this in CPP using Microsoft Seal. Microsoft Seal is an open source homomorphic encryption library that implements like some of the popular FHE schemes. Okay, so first of all, I'm setting parameters like something like choosing public parameters and also private parameters, and I'm also choosing a scheme. And then, okay, so this is in this file, and I'm also setting up x equal to 2 somewhere in the code. And then what I'm doing now is I'm computing powers of x. So now here I compute x squared, x to the power 4, and x to the power 8. And if I run the code and decrypt x power 2, my expectation is I'm going to get 4, which is correct, and then x to the power 4, which should be 16, but it is not, and x to the power 8 is something. So what's wrong here? So in order to understand what is going on here, let's look at the underlying how encryption works in these popular FHE schemes. So most of these modern FHE schemes use some technique called ring learning with errors encryption. I'm not going to details, but at a high level, we take a message m, it could be a real number or an integer, and we convert it into something. So the green indicates a padding, and then we take the public key. Public key is like an uniformly drawn matrix from some distribution, and then I draw some noise from a distribution, and then I compute this arithmetic operation, which results in a ciphertext. So the ciphertext contains the message m, but it has some noise, which also is considered as an error from this the red noise. And I just want to point out that this is a probabilistic operation. That means if we run the same program 2 times, the noise will be different. We are not going to get the same noise that is required in order to make the FHE work. So if we look at the ciphertext, and if we do homomorphic operations in each on the ciphertext, like we can see that the noise will be grown proportional to the initial noises in the ciphertext, and the message underlying message will also change in proportion to what we are doing. For example, if we are adding, so the result ciphertext will contain m plus m prime and some noise which has grown in proportion to E1 plus E2. And if it is a multiplication, the noise growth would be much more than that. It would be proportional to E1 times E2. And while we are at it, let's look at the decryption. So decryption is a 2-step process in which we take a ciphertext and we use secret key to obtain a polynomial with some error, and then we do rounding off to get the polynomial. And in the second step, we call it decoding. We take the polynomial and retrieve the underlying message, which is an integer, for example. The idea is like as long as these noises in the ciphertext are less than some critical value, the decryption is going to be correct. So the noise budget is defined as like the difference between the critical value and the noise in the ciphertext. And I just want to point out that like in the first point, like if we want to compute the noise, we need to decrypt the ciphertext. So that means that it requires access to the secret key, and it is totally undesirable in FHE applications. So let's look at the previous example. So this is as it is. Now what I'm doing is I'm adding a partial decryption in order to compute the noise budget in each step. So if I run the program again, I can see that x square has 18 bits, so enough noise budget, and in the next steps there is no noise budget. So that means that the computation we get from decrypting x power 4 and x power 8 are going to be incorrect. Again, the numbers changed in x power 4 and x power 8 because it's a probabilistic scenario. So every run we get like a different value. Okay, now I change the noise budget. So I changed some parameters. Like this is a public parameter. I changed from 40 bits to 200 bits. I rerun the same program, and I can see that we have sufficient noise, like non-zero noise. So I expect that the result should be correct. And it is in this case. So the first problem we wanted to deal was like how can we enforce correctness in the circuit, and here comes the basic types. So okay, we can see the entire scenario in this lattice. I would like to point that like it is a two-dimensional lattice, and there is a reason for it. I will come back to this. So each point in the lattice can be thought as a type. So for example, if we have a variable of type 10 and we have another variable of type 30, and if we add them together, the result will be of type 40. And with more and more homomorphic operations, the noise grows, and once it goes beyond the critical value, we don't get any valid decryption. Okay, this is our key insight for now. We propose like ILA, an intermediate language for arithmetic circuits, with this key insight that like the noise can be tracked using expressive types, and the theorem we have is well-typed programs are functionally correct. That means that if we decrypt them, we should be getting correct result. In other words, like before going further, I would like to explain what FHE correctness is like. So if we have data m1 to mn, and then we run some arithmetic operations on these variables, and we get like some result, and instead of running this, we run a parallel equivalent circuit f. So to do this, we encrypt it and we run the circuit f, which is equivalent to f message, and then we decrypt. We get like we should be able to get the same result. And in other words, like the FHE correctness is that like this diagram computes. Okay, right. What's the story? Like there is more to that story. So let's take the same example and rerun with a different value of x. Okay, I have. Okay, again, the noise are different because it's a probabilistic program. So the expectation is like the first result would be 400, and the second is 1600, and the last one is 16,0000 squared, which is 256 8 zeros. But that is not the answer. So what's going on here? So we can see that even within a sufficient noise budget, output can still be incorrect. This is because the plain text, like the polynomial we saw in the decryption, can only support a certain range of numbers. If the underlying message in the plain text goes beyond that range, we will get like a different kind of overflow errors. So again, we go back to the lattice. We can see this as like alpha is can be considered as a bound on the values. So the bounds are like it's a tuple. The first one says that it's the interval in which the underlying message lies, the underlying message in the ciphertext lies, and the second component is like the noise in the ciphertext. So for example, if we take a minus 10, 10, the interval minus 10 and 10 says that like the underlying message in the ciphertext lies between minus 10 to 10, and the ciphertext has a current noise level 10. So we do arithmetic operations, we go up the lattice like before, and you can see this like each point can be seen as a type in the PL perspective, and if we go beyond certain limit, we get like incorrect answer. So okay, now The solution is like, okay, we can come up with a language to solve, to track these noises, like using types. But then, what is the problem? Like, we have different FHE schemes. So, are we going to come up with a language for each FHE scheme, or can we do better? And the idea is ILA models. Like, so ILA is intermediate language for the arithmetic circuits. So again, it tracks. So ILA language so far described is expressive enough to capture all these overflows. But we wanted to more, and then the challenge is like we would like to address the correctness to more schemes, and that is where we present like ILA. So here ILA is parameterized by a model. A model is an abstraction of FHE schemes. And as long as an FHE scheme satisfies the axioms of our model, we can functional correctness comes for free. And we track noise without using secret key. So that and we do that like during the static time, during type checking. So it means that like writing correct FHE programs is much more simpler using ILA. And we have an implementation we instantiated for like a BGV scheme, and then we also have automatic noise management. I will come back to that later towards the end. So what is an ILA model? ILA model is like an abstraction of an ILA scheme, FHE scheme. In general, FHE schemes has like a set of public and private parameters, and the variables which are like a kind of sorted into messages, plain and ciphertext. And then our contribution is like we attach bounds to each of these sorts. And also we also define a partial order on that, and hence we have the types which are the sorts with bounds. So bounds usually tracks the overflows, and if and the partial order says that like if the bounds are beyond certain limit, we cannot guarantee functional correctness. And in order to define functional correctness, we want to define like similar operations on FHE operators. So in ILA, operators are abstracted as these three maps. And the first map says that like operator is like defined on n, takes n variables and comes up with one result. And the second says that like there is for each operator there is a corresponding operator which can be run on the unencrypted data. So these two actually they come from the theory of the underlying FHE scheme. So this is kind of an axiom. We call it as commutativity axiom in our model. And the last one is our contribution, where we have a computation to find the bounds of the result of after applying the operator. So let's look at an example. So operator could be O plus, which the O plus adds 2 ciphertexts and gives us 1 ciphertext. And this is like the equivalent of operator on the plain text. The clear text is usual addition, like integer or real number addition. And then, okay, I will show one example in the next slide. So the last map is only defined as long as if alpha is valid. So alpha is the bound which is valid if and only if there are like no overflows. And the map is not defined if the result has overflows. And then we have this commutative diagram, which is like correctness for the operator, and this comes from the theory of the correctness of the underlying FHE scheme. So in abstract, these are the specifications of our ILA model, and we can instantiate our ILA model for like most of the absolute FHE schemes. So BJV is one of the popular FHE schemes. Q and T are some public parameters. I'm not going to details. So ILA BJV is our instantiation, which we have implementation on top of the C library. So this is like a cipher. The third point is like a map defined for the cipher sorts. So so we take a ciphertext and we compute the bounds alpha. Here I would like to point out that like the alpha can be computed like without any help from the programmer, like a developer. It can be inferred, like it can be approximated using some noise approximation models. But the only place where we might need help from the programmer is defining the specifications of inf and sup. So that is because that talks about underlying encrypted message, which by looking at the ciphertext we cannot infer that. So this is the only place where we need help from the developer, and everything else can be automated. And the bound on the operator, the bound map on the operator is defined this, like it takes alpha 1, alpha 2. Alpha 1 and alpha 2 are like inf 1, sup 1, epsilon 1, and then there is like ILA BGV is again parameterized by how we compute inf, sup, and epsilon for the homomorphic addition. Again, there are like some estimations how we can estimate the noise after in the ciphertext after homomorphic operations. Like there is a lot of theory from cryptography. We can actually use it. So that means that if there is a better approximation, we can just throw away existing approximation and plug that in, and we get like a better performance. And we have the typing rule, which says that an well-typed operator is well-typed if it has correctarity and each expression is well-typed. That means that like there are no noise overflows and the result is valid. That means the noise after the computation, or the bounds after the computation or after applying the operator has no overflows in that. And then assuming this, like the commutative axiom is like just a commutative axiom of the operators we saw earlier, and downwards closed axiom is some other assumption which says that like the noise growth is monotonic. And these two axioms are satisfied by most existing FHE schemes. I would say like if it is not like either of the like if an FHE scheme like doesn't satisfy either of these two axioms, I would say it's incorrect. And then we formalize correctness as a message equivalence, which was like running a circuit on the clear text is the same as running an equivalent circuit on the encrypted data and then decrypting it back. And further, we also have noise management. So most of these FHE schemes have like something called noise refresh operators. What it means is like once we have exhausted noise, like we can place like some operations like bootstrapping or modulus switching. Those take like ciphertext and refresh noise. So they keep the underlying message as it is and reduces the noise in the ciphertext and gives us that. So placing these noise refreshing operations, like these have the same drawbacks as the initial, like the programmer needs to guess where overflows might occur or periodically use the secret key to decrypt it and look the noise overflows. So which is like impractical in real world, and hence we have an inference algorithm which kinds of places the noise refresh operators like at an optimal place, and the advantage is two-folded. One is like the programmer need not to worry about like any of this stuff, and we can optimize the noise placement operator because we are just taking away the guesswork away from the programmer. And we have the soundness. So soundness says that like noise overflows do not happen in a well-typed ILA program, and this is based on a condition that like the noise modeling the underlying noise modeling we use is over approximation. If the over approximation is not correct, like we cannot have soundness. So, but our ILA model is not complete. That means that the type checker still rejects the programs which are otherwise like correct. And we ran some experiments. We saw that like our ILA BGV type checker like matches with the seal's multiplicative depth. So multiplicative depth is a measure to measure how many operations certain parameters can do. And we used Smart's noise estimation, Nigel Smart and his student Anna. So here is the evaluation we came for the BGV. So the blue dotted line indicates the programs, the multiplicative depth computed using ILA BGV. So ILA BGV just looks at the initial parameters and the variables and computes say that, hey, these are the many multiplications you can perform on this encrypted data. And then we run the same example in SEAL by decrypting it and computing like how many multiplications the SEAL allows the same example to do. So we can see that almost all of the times we have the same multiplicative depth, but at certain cases like the blue dots, like we have ILA rejected is like more strict, rejected more valid programs. But the difference is just 1. Like there is like ILA's multiplicative depth is, predicted multiplicative depth is 8, and then the seals was 9. On the right hand side, we have the graph which represents the multiplicative depth computation using using ILA's inference algorithm for modulus switching. So seal doesn't support bootstrapping, so we didn't had a chance to test bootstrapping. So we only tested for modulus switching. And here we can see that like the results are more or less like plus or seal exceeds ILA's multiplicative depth by only 1 multiplication. And there is like 2 dotted lines as we go up to the top right corner. That is because the encryption and decryption is a probabilistic. Depending on the initial noise, there are cases where multiplicative depth is like a 9, and if we rerun the program, the multiplicative depth was reduced to 8. So that was the 2 lines, the top right corner and the right diagram. And with this, I will take any questions. Thank you.
Thank you for the talk. Are there any questions?
Yeah. So ILA, so I assume like the new FHE scheme has like all the correctness properties proved. So ILA is like abstracts it out. Like so you don't have to. It just fits in ILA. Like we don't have to do any implementation. The only thing, like if there are like a new operations, we might have to add them to the type checker. So other than that, like we don't have to do anything.
So is that like a day of work, a week of work, a month of work?
It shouldn't be like maybe a week of work, like not much more than that.
Okay.
But like the hard part is like there should be some computations on like the noise bounds. Like if the operator, like you come up with a new operator, we need to know some estimations on the noises at the bounds after like in the result. So if there is such result, then it shouldn't like take more than a week. I would say less than a week.
Okay.
But the hard part is like modeling the noise after applying the operation.
Cool. Thank you.
Any other questions?
Any more questions?
Yeah, thanks again for the talk. I was wondering if you could say a bit more about the type system, because like you're tracking seems like you're tracking fine-grained properties. Like are you using some kind of refinement types, or like how does the type system look like?
Very kind of very low level refinement types, but it's just like just basic types. I mean, we don't even need refinement types. We want to support approximate schemes, like we might need refinement types. But I can show you type system. But okay, I think I can share it. Type system, can I share type system now? Oh yeah, maybe not. It's under review, but like I can talk about the type system later. But it's just like a very basic.
Okay.
Yeah.
Oh.
I can add a little bit more to that answer on the type system. So types have bounds, so they're very similar to refinement types, except that there are no variables in that, so we do not have to dispatch it off to any SMT solver or anything. So everything is like very unified. It can be unified like within the type checker. But as Ram mentioned, if we can support a new scheme that is approximate in nature, that brings in like probabilistic nature, so that's when we will actually use the full power of the refinement types. At the moment, it's pretty basic.
To my understanding, LWE kind of based crypto systems are also used in other kinds of cryptographic primitives. Do you have plans to look at those things as well, or is this like something well suited for
maybe
FHE?
that is the question for Brian, because actually this project was like we tried to add FHE to OWL. Then we thought like maybe we shouldn't like keep it as it is. I think like Josh at some point like he had plans to add LWE to OWL. So we don't like plan on doing that in this project, but Josh does have plans to extend OWL with LWEs.
Yeah, not so much FHE, but like multi-party computation, of various sorts, or like
That's
PIR.
a long-term goal, but not
Okay.
not anytime soon.
Great, thanks.
Okay, thank you.
Okay. Yeah.
Hi, I maybe missed a bit of the context. When they want to use a FHE scheme that adds noise versus one that doesn't make noise?
So if it doesn't add noise, then the encryption would be deterministic. So that means like a simple for loop can break the encryption. So you can, like if you encrypt like one variable, like let's say if you encrypted 2, you will get like the same ciphertext all the time. So you can just match up, or you can like write a for loop for and the integer values from like -2 to the power like whatever it is, and run it and compare the ciphertext, and then it breaks like the underlying encryption.
So in practice, people always use the noise.
Yeah, so it's the noise is what it makes the scheme hard to break.
Okay, thank you.
Otherwise, it's deterministic and it can be break.
Okay. If there are no more questions, then let's thank the speaker.